Central 9.2 central limit theorem for sample means. Applying the central limit theorem for sample means to calculate the probabilities. Describe the features of the t-distribution. Central limit theorem for sample means. If certain conditions are met, the central limit theorem assures us that the distribution of the sample mean follows an approximately normal distribution, no matter what the shape of the population distribution. Okay, this assures us that the distribution of the sample means follow an approximately normal distribution, no matter what the shape of the population is. Conditions to check when determining whether you can apply the central limit theorem. To analyze data, consider the following conditions: a random sample and independent. Each observation is collected randomly. Each observation is connected randomly from the population. The observations are independent of each other. One doesn't affect the other. Large sample. Either the population distribution is normal or the sample size is large. Usually 25 is large enough. If the sample is collected without replacement, the population must be at least 10 times larger than the sample size. If the three conditions are met, then the sampling distribution of the sample mean is approximately normally distributed. Okay, and there's your mu, and there's your standard deviation there, or standard error. The larger the sample size, the better the approximation. If the population is normal to begin with, the sampling distribution is exactly a normal distribution, regardless of the sample size. Visualizing distributions of the sample mean. So here shows the distribution of the in-state tuition and fees for all your two-year colleges. Note that they're skewed and multimodal. Okay. The figures below show the distribution of the sample mean for sample size 30 and size 90 drawn from the skewed multimodal on the previous slide. So they took samples from this. They took samples from this um, population here. When they took samples of it, it turns out to be normally distributed. Sample size 30 and sample size 90 is even more. Okay. Notice that uh, each is approximately a normal distribution, and the standard error decreases as the sample size increases. See 90, 30. So the standard error, in this case here, standard deviation, standard error between the samples decreases. An example here, we have weights of 10-year-old boys. According to data from the National Health and Nutrition Exam Survey, the mean weight of 10-year-old boys is 8.88.3 pounds with a standard deviation of 2.06 pounds. Assume the distribution of the weights is normal. Suppose we take a sample of 30 boys from this population. Can we find the approximate probability that the average weight of the sample will be above 89 pounds? If no, find it. If not, explain why. Suppose we take a random sample of 10 boys from the population. Can we find the approximate probability that the average weight of the sample will be above 89 pounds? If so, find it. If not, explain why not. So, looking at A part again. So we take a sample of 30 boys from the population. Can we find the approximate probability that the average weight will be above 89 pounds? If so, find it. So we have a random sample here. and the population is at least 10 times larger than the sample. Okay, and the population is normal, so we can apply the central limit theorem. The distribution of the sample means is this here, where you have your mean and your standard error. You can use technology to find the probability that the mean is greater than 89 pounds. So here they did how they did it with to find that standard error there. So the standard error was found to be 0.3761. And we have the mean, and we wanted the probability that it's going to be greater than 89, and that's your probability. That's using StatCrunch. B, suppose we want to take a random sample of 10 boys. Can we find probability? The average weight of the sample will be above 89 pounds. We have a random sample. The population is at least 10 times larger than the sample, and the population is normal. So we can apply the central limit theorem, even though the sample size is less than 25. The distribution of the sample means is here. We have your mean and your standard error. So you use StatCrunch again. You have 88. There's a standard error. Probability that it'll be greater than 89 comes to be here. Notice that the probability is different from A due to the larger standard error in the distribution sample of size 10. So you have a smaller sample, you have a larger error. And that's using StatCrunch there. Another example here. Home prices in a certain community have a distribution that is skewed to the right. The mean income of the house home prices is 498 on 498,000 with a standard deviation of 25,200. Suppose we take a random sample of 30 homes in this community. What is the probability that the mean of this sample is between 500,000 and 510,000? Suppose we take a random sample of 10 homes in this community. Can we find the approximate probability that the mean of the sample is more than 510,000? If so, find it. Okay. So we took a sample of 30 homes in the community. What is the probability that it'll be between? Okay, we have a random sample. Sample is large, more than 25, and the population is large. Okay. So we pass. It meets the central limit theorem, so it's normally distributed with a mean and a standard deviation here. So in this case here, they use StatCrunch and they use between. They give us the mean and there's a standard deviation. And they want between 500,000 and 510,000. And there's a probability there. And they did this with StatCrunch. Another example with home prices. Suppose we take a random sample of 10 homes in the community. Can we find a probability that it's more than 510,000? If so, find it. If not, because the population of the home prices is skewed, we would need a sample size of at least 25 to apply the central limit theorem. Since the sample size is 10, we cannot find this probability. Identifying the distribution. The next slide shows three distributions. One of them is the population. The other two are approximate sample distributions. The sample means randomly from population. One sample size 10, the other is 25. Match the graph with the correct distribution. this first one here, this one here. The central limit theorem tells us that the sampling distribution for a sample, uh, for the sample means it's approximately normal. There. The central limit theorem tells us that the sampling distribution for a sample means are approximately normal. Since this graph is not approximately normal, this is a graph of a population. Okay. As the sample size increases, the standard error, the spread of the data, decreases. Since figure A has more spread than figure C, A has distribution of size 25 and C is a distribution of size 10. As the sample size increases, the standard error of the spread of the data decreases. Since figure A has more spread than figure C, figure A has a distribution of size 10, figure C has a distribution of sample size 25. Now, hypothesis tests of confidence intervals for estimating and testing the mean are based on a statistic called the t-statistic. So we're testing the mean, not a proportion this time here. They're doing a t-statistic. Okay, which is similar to the z-star here, where we knew the standard deviation. Since the population standard deviation is almost always unknown, we divide by an estimate of the standard error using the sample standard deviation. Okay, so there's your formula for the t-statistic. The t-statistic does not follow the normal distribution because the denominator changes with every sample size. The t-statistic is more variable than the z-statistic, whose denominators are the same. If three conditions hold for the central limit theorem, the t-statistic follows a distribution called the t-distribution. Okay. It's symmetric in bell shape, has thicker tails than the normal distribution. See, it has thicker tails than the normal distribution. The shape depends on degrees of freedom. If the degrees of freedom is small, the tails are thick. As the degrees of freedom increase, the tails get thinner, and it becomes more normal, like a normal distribution as the degrees of freedom increases.